Hello and welcome again to a new lesson of Dr. Christoph from Phayao University. Today I would like to talk with you about reactions of transition metal complexes. The reactions of transition metal complexes are interesting, especially when we look at catalytic reactions. To understand the catalytic properties of transition metal compounds, we should understand the basic steps. The basic steps or elementary steps of reactions. So lucky for us, there are only 3 basic steps we have to consider. One of them is the substitution. Substitution of ligands or replacement of ligands at a transition metal compound. The other 2 are more complex. One is called oxidative addition, and number 3, insertion. These 2 reactions are more complex and we will discuss them in the next lesson. Today we will talk about substitution reactions. Ligand substitution reactions can occur in principally 2 ways. One way is the so-called dissociative way. So we have a metal complex with the ligand X, and the first step in this reaction would be the dissociation of the X ligand, and then in the consequence we have another ligand Y, which will then attach to the metal, so we can get YMLN plus X. So again, this is the dissociative pathway, or D. First, the bond between metal and the ligand is broken, and then a second ligand can replace the first one. The other way would be associative. In this case, the first step would be the approach of a second ligand and the formation of a big compound with one more ligand, and in the consequence one of these will go out and X is replaced by Y. So we have these 2 extreme cases. In the reality, normally we are in between these cases. And beside these 2, we have a so-called interchange mechanism, called I. In this mechanism we have something in between, so we could write it like this. We have a compound and another ligand, and they form a kind of association, but it's not like a full YM bond or XY bond. We can think of it is like an SN2 reaction in organic chemistry. When the ligand Y comes close to the metal, then kind of bond is build it up here, and the second time the MX bond loses, becomes broken, and finally we get our substitution. So this interchange mechanism, you could remember, is similar to a nucleophilic substitution type 2 in organic chemistry. That also means we have an inversion of the stereochemistry. Okay, now the reality unfortunately is more complex. In the reality, we have always an interchange mechanism. It's unlikely that something like this happens because the ligand Y is always present around our molecule and it will be in contact in some interaction with the metal always. So in the reality we would not say we have dissociative or associative, but rather we would have an interchange mechanism which tends to be dissociative, or an interchange mechanism which tends to be associative. Okay, what do I mean with that? Dissociative means that the rate limiting step is the dissociation. So again, we have this kind of reaction. The ligand Y comes close to the metal, and then the metal X bond becomes loose. And this loosening leads finally to the breaking of the metal X bond. And this final step here, this is the critical step. This step determines the reaction rate. Sorry, plus X. Again, in the ID mechanism, the rate determining step is the breaking of the metal X bond. And I associative is the other way around. Here, the first step forming this bond, the YM bond, this step now is the critical step to form the bond between metal and Y. Is the slow process which determines the reaction speed. In the consequence, the breaking of the MX bond is fast. So this reaction is fast, whereas in this case the first reaction is fast. Okay, I give you a concrete example for the ID mechanism, which is more common, is called the Eigen-Wilkins mechanism, because these two people find out the kinetic of this reaction step. Okay, we have an example. If we look at the hexa-aqua compound complex of nickel 2+, and we add another ligand like ammonia, then what happens first is we create in solution a kind of so-called encounter complex. So we write it like this, and this is called the so-called encounter complex. It cannot be isolated and it has a very short lifetime. And in this encounter complex, now this is formed very fast. This is a fast equilibrium, and we can describe it with the equilibrium constant Ke. And in this encounter complex now can happen the real exchange, and this exchange of water against ammonia is a slow process. So the breaking of the nickel-water bond is slow, and finally we get the penta-aqua amine compound and water, 2+ of course, water. So this equilibrium constant K can be expressed by the concentration of this encounter complex. I just make it short, I just write Ml6 and Y. General case, divided by the concentration of Ml6 multiplied by concentration of Y on the left side, Ml6 and Y. Now this reaction from here to here can be described by the reaction rate. R is multiplied is the speed constant K, small k, multiplied by the concentration of this strange encounter complex. Now we can combine these two equations because we can never measure the concentration of this encounter complex. We can combine these two equations and then we come up with the reaction rate with the speed constant multiplied by this PA multiplied by the concentration of the total concentration. This plus this plus this, the total concentration of the metal compound multiplied with the concentration of Y divided 1 plus PA multiplied by concentration of Y. So then we end up with this reaction equation, and in the case if Y concentration is low, what is normally the case, then we can assume that this product PA multiplied by concentration Y is much smaller than 1, and that means in this case we can omit the denominator. So this simplifies our equation. The reaction rate is speed constant multiplied by the total concentration of metal compound multiplied by total concentration of ligand. So this is a reaction, first order reaction, and we can determine this by measuring the concentration, for example the remaining concentration of Y over time. If we know it's a first order reaction, then we can find K from our measurement. Characteristic for the ID mechanism here is now, if we have the same metal compound and we let it react with different kind of ligands and we measure the K for the substitution reactions and we find that the K is more or less the same for all these ligands, it does not vary a lot, then we can be quite sure that the mechanism is dissociative, because the slow process is the breaking of the nickel water bond. So the new ligand, the nature of the new ligand does not have a big influence on this slow step. And the rate constant K that we measure here in the experiment again depends on the concentration of our metal compound and the new ligand. And this observed K is not the real K. The real K is actually, what we observe is the product of the real K here multiplied by the equilibrium constant. Okay, finally, how can we get this pre-equilibrium constant Ka? Now there again were two clever people named Fuss and again Eigen. They give us an estimation method to estimate this equilibrium constant Ka. And this estimation is based on the Coulomb attraction between the ligand and the metal compound. So they get a formula. This is like the volume of the sphere. A is the distance between the metal and the new ligand in the encounter complex, multiplied by Avogadro number, that means by the total number in 1 mole. And now the Coulomb term is E power minus V divided by K and temperature, Boltzmann constant and temperature. And this V is like a Coulomb Coulomb term. Okay, we don't need to understand this 100%. We can just know that this V will be 0 if ML N or Y is neutral. So in the case of NH3 and hexa aqua nickel 2+, this V would be just 0. And then this term will disappear, and then the Ka depends only on the distance between the nickel and the new ligand, in this case ammonia. Or this V will become negative, and negative is positive. That means this term becomes very important. This V becomes negative when MLN and Y have opposite charge. So for example, Cl- plus nickel hexa aqua compound, opposite charge minus plus, and then this V term becomes negative, and then it has a big influence on this K. That means the K will become much bigger, minus plus, when we have opposite charges. And this is also quite logic, because these two molecules will attract each other much faster and will be much more on the side of the encounter complex than the neutral molecule.